Welcome to Omni Eyes. Today, we explore the incredible hoverfly, a tiny insect that masters the complex art of absolute stillness perfectly. Have you ever seen a hoverfly suspended in midair, completely motionless, as if hanging by an invisible, magical silver spider thread quietly? Despite unpredictable wind currents and chaotic environmental changes, this remarkable creature remains perfectly locked in place, without a single noticeable drift ever. How does this tiny biological machine achieve such flawless aerial stability when even modern drones struggle against sudden, unexpected wind gusts daily? The secret lies within its massive, highly evolved compound eyes, which constantly monitor every single microscopic change in the surrounding natural environment. This fascinating biological phenomenon is known as optical flow, a complex visual processing system that calculates motion with absolute mathematical precision continuously. As the environment shifts around the insect, its brain rapidly processes these visual cues to determine its exact spatial position almost instantly. Every tiny movement of a leaf or blade of grass is registered, allowing the insect to adjust its wings with absolute perfection. The hoverfly processes this vast amount of visual information in mere milliseconds, making it one of the fastest biological computing systems alive. It is essentially a living sensor, calculating millions of data points simultaneously to maintain its fixed position in the highly turbulent air. To understand this miracle of nature, we must look closely at how modern camera technology attempts to replicate this exact behavior perfectly. Filmmakers and photographers have always battled against unwanted camera shake, which ruins beautiful shots and creates highly distracting, blurry video footage constantly. Early attempts to stabilize cameras involved heavy, cumbersome mechanical rigs that were extremely difficult to operate and totally impractical for fast movement. The solution eventually came in the form of the electronic gimbal, a brilliant device designed to keep cameras perfectly level absolutely everywhere. A modern gimbal uses sophisticated gyroscopic sensors to detect any unwanted rotational movement across 3 distinct axes in real time, almost instantly. The moment your hand shakes or tilts, the sensor detects that precise movement and sends a rapid signal to the internal motors. These powerful, brushless motors immediately generate an exact opposing movement, effectively neutralizing the shake before it can affect the sensitive camera lens. This technological marvel allows filmmakers to run, jump, and climb while capturing incredibly smooth, cinematic footage that looks professionally stabilized almost always. However, long before human engineers invented the electronic gimbal, the humble hoverfly had already perfected this exact same stabilization technique completely naturally. The insect brain acts as the central processor, while its incredibly fast wings function just like the highly responsive motors of gimbals. Whenever a sudden gust of wind pushes the insect slightly off course, its optical flow system almost immediately detects the unwanted shift. The brain calculates the exact amount of force needed to counteract the wind, sending rapid electrical signals to the insect flight muscles. The wings adjust their pitch and speed in a fraction of a second, pushing back against the wind with totally equal force. This continuous cycle of detection and correction happens hundreds of times per second, creating the beautiful illusion of absolute stillness in midair. It is a flawless biological feedback loop, far more efficient and responsive than any mechanical stabilization system currently built by human engineers. Scientists and engineers have spent decades studying the hoverfly, hoping to unlock the deep secrets of its incredible aerial stabilization abilities today. By analyzing the specific neural pathways involved in optical flow, researchers are currently developing smarter, more responsive algorithms for autonomous flying drones. These advanced biological drones can navigate through dense forests and chaotic urban environments with the same effortless grace as the tiny insect. They use advanced optical sensors to map their surroundings dynamically, constantly adjusting their flight paths to avoid obstacles and maintain perfect stability. The hoverfly teaches us that sometimes the most advanced technological solutions can be found by simply observing the natural world very closely. Nature has spent millions of years refining these complex systems through the rigorous, unforgiving process of evolution and natural survival selection daily. Every single detail of the unique hoverfly anatomy has been optimized for perfect flight, from the shape of its wings to eyes. The compound eyes are particularly fascinating, composed of thousands of individual microscopic lenses that capture light from almost every possible viewing angle. This panoramic vision allows the insect to monitor the entire landscape simultaneously, ensuring that no sudden movement goes completely unnoticed by it. When the background appears to move backward, the insect knows it is moving forward and instantly adjusts its wings to completely stop. This precise calculation of relative motion is the core principle of optical flow, a brilliant concept now heavily utilized in computer vision. Autonomous modern cars use similar optical flow algorithms to track moving objects, calculate safe distances, and navigate smoothly through heavy city traffic. Virtual reality headsets also rely on this technology to track head movements accurately, providing a seamless and immersive digital experience for users. It is truly remarkable to think that such advanced modern human technology shares its fundamental operating principles with a common garden insect. The hoverfly does not need massive batteries or complex silicon microchips to perform these incredibly demanding mathematical calculations in real time, constantly. Its tiny brain, no larger than a grain of sand, processes all this visual data with astonishing speed and absolute biological efficiency. This extreme biological efficiency is something human engineers still struggle to replicate, as our machines require vast amounts of electrical power always. Imagine a future where tiny robotic drones can fly indefinitely, powered only by the minimal energy required to run biological optical sensors. These miniature drones could be used for critical search and rescue missions, navigating collapsed buildings with the agility of a real hoverfly. They could monitor agricultural crops, precisely identifying pests and diseases without the absolute need for harmful chemical pesticides or heavy farming machinery. The possibilities are endless when we learn to harness the profound wisdom hidden within the intricate designs of the beautiful natural world. As we continue to push the boundaries of modern engineering, biomimicry will play an increasingly vital role in our future technological advancement. The hoverfly is just one of countless examples of how nature has already solved some of our most complex modern engineering challenges, from the aerodynamic shape of a bird wing to the incredible structural strength of a spider web. Biological inspiration is truly everywhere. We simply need to open our eyes and observe these tiny miracles with the same focused attention as the brilliant hoverfly itself. Let us return to the fascinating mechanics of the insect wings, which are fully capable of beating hundreds of times per second. This rapid wing beat creates a powerful downward thrust, allowing the insect to defy gravity and remain perfectly suspended in the open air. But generating lift is only half the battle. The insect must also control its pitch, roll, and yaw with extreme flight precision. It achieves this by constantly altering the angle of attack of its wings, making microscopic adjustments with every single rapid stroke consistently. These subtle changes in wing geometry allow the hoverfly to dart forward, backward, or sideways with astonishing speed and absolute directional control. When hovering, the wings trace a complex 8-shaped pattern in the air, generating a highly stable vortex of lifting aerodynamic force. This unique wing motion is incredibly difficult to simulate mechanically, which is why most human drones still rely on spinning plastic propellers. Propellers are highly efficient for straightforward flight, but they lack the dynamic agility and precise control of a biological flapping insect wing. Researchers are currently experimenting with flapping wing miniature vehicles, attempting to replicate the hoverfly unique aerodynamic properties for better indoor flight stability. These experimental machines face immense engineering challenges, particularly in developing lightweight materials capable of withstanding such rapid and continuous intense mechanical stress. However, the potential rewards are massive, as true biological-inspired flight could revolutionize how we explore and interact with our surrounding environment. Just as the camera gimbal transformed filmmaking by providing unprecedented stability, biological drones could transform industries from logistics to vital environmental monitoring. It is fascinating how the pursuit of capturing a smooth, perfectly stabilized video shot led us to understand complex natural biological systems. The desire for visual perfection drove human engineers to create the gyroscope, a spinning wheel that naturally resists sudden changes in orientation. Early gyroscopes were massive and mechanical, used primarily for stabilizing large ships and guiding early aircraft through thick, blinding storm cloud cover. Today, thanks to micro-electromechanical systems, we have incredibly precise gyroscopes, small enough to fit comfortably inside a standard modern cellular smartphone device. These microscopic sensors detect the slightest rotation of your phone, allowing the screen to automatically adjust its orientation with flawless visual accuracy. They are the exact same sensors used in modern camera gimbals, providing the crucial data needed to counteract unwanted human hand movements. In a way, these tiny silicon chips are the technological equivalent of the Hoverfly highly sensitive, incredibly fast biological complex visual system. Both systems rely on continuous data collection and rapid processing to maintain a stable equilibrium in a constantly shifting, chaotic natural environment. The main difference is that the Hoverfly achieves this incredible feat using organic neurons and muscles instead of silicon chips and motors. As we marvel at the smooth cinematic footage captured by a modern drone, we must acknowledge the profound biological inspiration behind it. Every sweeping landscape shot and perfectly tracked action sequence owes a massive debt to the evolutionary perfection of the tiny, humble Hoverfly. The next time you see one of these remarkable insects hovering over a flower, take a quiet moment to appreciate its mastery. You are looking at nature's ultimate gimbal, a biological machine that has perfected the complex art of stabilization over millions of years. It stands as a profound testament to the incredible power of evolution to solve the most difficult physical challenges with absolute elegance. The detailed study of optical flow in insects has also led to significant advancements in the field of modern artificial intelligence development. Machine learning algorithms are now being trained to process visual data in ways that closely mimic the complex neural pathways of insects. These neural networks can quickly identify patterns and calculate motion vectors much faster than traditional, rigid computer programming methods ever possibly could. By copying the Hoverfly efficient visual processing, artificial intelligence can become far more responsive and adaptable to sudden, unexpected environmental changes globally. This is particularly important for the development of autonomous robots that must navigate safely through unpredictable human environments without ever causing accidents. A robot equipped with biological-inspired optical flow sensors can easily detect a person stepping into its path and stop instantly, safely. It can also maintain its balance on uneven terrain, adjusting its mechanical limbs with the same rapid precision as hovering insect wings. The intersection of biology and technology is creating a new era of engineering, where the boundaries between natural and artificial completely blur. We are no longer simply building machines. We are slowly learning to grow highly complex, adaptive systems directly inspired by living organisms. The Hoverfly, with its perfect stillness and lightning-fast reflexes, serves as a brilliant guiding light in this exciting new scientific frontier. It reminds us that true innovation often requires us to look beyond our own human inventions and deeply study the natural world. The answers to our most difficult engineering problems may already exist, quietly buzzing around our gardens and forests on warm summer days. We just need the patience and humility to observe them closely, to understand the deep wisdom encoded in their incredible biological structures. As this series comes to a close, we sincerely hope you have gained a new appreciation for the hidden wonders of nature. From the microscopic world to the vast cosmos, there is always something new and incredibly fascinating waiting to be completely discovered daily. The story of the Hoverfly and the camera gimbal is just one beautiful example of the profound hidden connections that surround us. Science and nature are not separate entities. They are deeply intertwined, each providing valuable insights that help us fully understand the other. By studying the natural world, we can build better technology. And by using advanced technology, we can better understand deep natural mysteries. This beautiful cycle of discovery and innovation is what drives human progress forward, pushing us to explore further and learn much more. We encourage you to step outside, look closely at the world around you, and find your own special moments of absolute wonder. Whether it is a hoverfly suspended in midair or a perfectly stabilized cinematic drone shot, breathtaking beauty is everywhere if you look. The principles of optical flow and absolute stabilization are constantly at work, quietly shaping the physical reality we humans experience every day. Embrace this incredible knowledge and let it inspire you to see the ordinary world through a completely new and utterly fascinating lens. Remember that even the smallest, seemingly insignificant creature holds deep secrets that can completely revolutionize our understanding of modern science and engineering. Thank you for joining us on this incredible journey through the fascinating intersections of biology, advanced technology, and the wonders of nature. We have explored countless mysteries together, uncovering the profound brilliance hidden within the intricate designs of the natural world completely around us. As we conclude this final episode, we leave you with the inspiring visual image of the hoverfly, a true master of stillness. May its perfect balance and unwavering stability inspire you to find your own center in a constantly moving and highly chaotic world. This is OmniEyes, signing off for the final time. Stay curious, keep exploring, and never stop marveling at the vast universe.